Hello, I'm Papleting, and in this video I'm going to be showing you how to use the ProtoGraph programming language to simulate this bouncing ball inside of Resonite. We'll be covering everything from setting up your development environment to the general workflow moving back and forth from the text editor to Resonite. Be aware though, this is not going to be covering the absolute basics. I'll be moving quite quickly through material, so I'm assuming prior knowledge of ProtoFlux, Resonite, as well as general programming concepts. Before we jump into programming, you're going to need a couple of dependencies to get started. The first one is the .NET SDK. This will allow you to run the .NET CLI tool to be able to compile your ProtoGraph. You're also going to need the Flux SDK tool. You can install it using the .NET CLI using this command here. And then you're going to need a text editor. VS Code, as you can see here, is perfectly fine. I have the .NET SDK already installed, 9.0. And then I'm going to check the Flux SDK, which will be installed on your command line path as well, and I have version 0.18 installed here. So make sure you have both of these accessible. Additionally, recommend installing the ProtoGraph extension from the VS Code extension store. This will give you all of the autocomplete and on-hover information. Do be aware that you might need to adjust a setting to point to the correct Resonite DLL location on your system. I'd also recommend to create a VS Code task file. This will help make the development process faster when you want to compile your ProtoGraph. So for example here, if I make a bouncing ball module and we'll just make it empty, when we go and compile it, it will use that task and generate our brson file for us. We can then add to this module, just do a simple display, add a couple numbers together, and then when we recompile it, it'll use that task again, and this time it will have 4 ProtoFlux nodes. Let's get right to the coding. We're going to modify that bouncing ball module with a new slot input, and we're going to call it ball, and then we're going to define an impulse, and that impulse is going to be calling set global position on the ball. You'll notice on the left-hand side, I have conveniently placed 3 pre-made modules for calculating the position, velocity, and quadratic roots. These can be used in the current module, and this allows us to get nested node behavior. Because Resonite doesn't have nested nodes yet, this is just inlining, but these nodes have their own inputs, their own outputs, and then their own internal definition. You can define your own too. I've just created these ahead of time. In this case, for current position, we're using named arguments. You could do positional, but for more complicated nodes, it helps to see what parameters are paired with what arguments. And then we'll just finish up defining the argument values. So gravity here is just a constant float. Some of the other ones like time delta are going to be defined in terms of other values and variables. We're going to define the start world time, for example, as a sync variable, which is a data model store. You could use a store, which is a stored value. Depends on if you want the synchronized behavior or desynced behavior. That's up to you. Now that we have our basic logic set up, we're going to need to do a little bit of initialization, specifically for these variables. We're going to need to set the start world time, the initial velocity, and the initial position. For now, hard-coded values are fine. We can specify whatever floats we want here. Keep in mind you have the x, y, z. Y is the vertical direction, so that's the height. And then the start world time will just be the current world time. Then we need some way to trigger this. For now, we can just set a timer that on some regular interval will reset it to the starting position so that the ball loops and we can see it as we debug. When we compile it, we will get our brson, our Resonite record. It will have 35 ProtoFlux nodes, and this file is the one we will import into Resonite. In Resonite, you are going to need the Flux SDK UI. This can be found in the ProtoGraph public folder. When we import our Resonite record, we can then inspect the Flux inside. Here I am using MudgePrint, but you can use your print system of choice. You can see how the nodes are laid out and connected. Also, you can use this to debug anything, but we're going to pull it out and assign it to the ProtoGraph slot. I've also spawned out a sphere and an inspector, and I'm going to drop that sphere slot into the ball element input. And our ball now moves. Perfect. But wait, what if we want the ball to bounce? Because right now it's just going to go through the floor and continue on indefinitely. This is where things get a little bit more complicated. Essentially, what we want to do is predict when the ball is going to hit the ground and figure out what the position and velocity of the ball at that moment in time is going to be, and use that to reset the start world time, initial velocity, and initial position with the updated trajectory information. To do that, we're going to calculate the current velocity in addition to the existing current position. We're also going to pull in the other predefined modules for calculating the projectile velocity and the quadratic roots. For the quadratic roots, we're going to use the gravity, but keep in mind we have to divide it by 2. And then we're going to provide the initial velocity and the initial position as inputs. In both of the cases, we're going to use the y field because for the impact time, we only care about the vertical position to calculate when it hits the ground. For the impact position, we're going to use projectile position again, but this time we're going to use the impact time instead of delta time. You'll notice here we have an error because quadratic roots actually returns 2 values. So to fix that, we're going to grab the minus root value off of the quadratic roots output. Then we're going to do a similar type of thing for the impact velocity. You can use the projectile velocity. We're going to copy the same stuff over, change it to impact time. Now we've done most of the setup related work. Next, we need to actually define what a bounce does. So we're going to define an impulse here, which is going to be a sequence of several things to do in sequence. We need to define a couple of temporary variables because we're going to be reassigning different variables. Here we're just going to have a new start time and a new velocity. And then we're going to do some calculations on the values we've defined above to get the new values. One of the things we're going to do is we're going to unpack the impact velocity and destructure it into the x, y, and z components. And then we're going to reflect it by keeping the x and z values the same, but we're going to invert the y value. That's what we're going to call a bounce. Now that we have all of our values, we just need to reassign all of the variables to their new values. So that backwards arrow just writes a value, and we're just going to do these one after the other. New velocity, new start time, new initial position, new world time. Do keep in mind the order does matter, so you have to make sure you do this properly so you don't write the wrong values at the right time. And then once we're all done, we're going to set the current position like we did before. But current position is defined below, so we actually have to move this above so that it can find it. Then we're going to move the local update down below. However, we don't want to set current position on every update. We actually need to modify this because sometimes we want to bounce, not always just set the current position. So we're going to set a couple of conditions. We want to check if it's below the ground and see if it's actually moving downwards. Do notice that the below ground and the velocity checks both only care about the y component. We don't care about any x or z velocity or positions, just the y, only the height component in this case. If both of those cases are true, then we do want to bounce. Otherwise, we just want to set the current position like we have already been doing. Next, we can go back into Resonite and replace our Flux. I'm going to pull out the bundle from MojiPrint, and then I'm going to import the new BouncingBall version. And what I want to do is assign the new one to replacement Flux, replace Flux, and this will overwrite the previous one with the new one. So you can see our ball now bounces. Our next complication is decay. What I mean by that is on every bounce, we actually want the ball to lose a little bit of energy. So it's going to slowly slow down. It's not going to bounce the same height every single time. Our decay in this example is just going to be a simple coefficient, and we're going to multiply it by the velocity when we reflect it so that the velocity decreases over time. I'll change a couple of our debug values, and then back in Resonite, we will update our flux just like we did before. If we look at the ball now, we'll see that it is decaying. It no longer has lateral motion in the X or Z direction, but the maximum height it attains will slowly decrease over time before it resets. Looking at the flux, we can see that we have all our values, and I can actually change the decay value here, so I can make it a bit larger, but in this case, I'll make it a bit smaller, so it should decay faster now. However, we still have a problem. The ball doesn't stay on the ground. It goes through the ground. So we need to fix that. We'll do that by changing the set current position to clamp the value if it's less than 0. So we'll add an intermediate step. And like with reflective velocity, we just care about the y component. So we're going to keep the x and z unchanged, but for y, we're going to get the maximum of y and 0. So it will never go below 0. However, we're not quite done yet. The ball's position is actually the center of it, not the bottom. So it's going to sort of stay halfway in the ground. To fix that, we're going to define a new input called BallRadius. And this will help us stay above the ground, so to say. And so instead of using 0 as our minimum value, we're going to change that to BallRadius. We do need to change a couple of other things. So we need to change it in the quadratic equation solving to make sure the impact position is calculated correctly. And then when we check below ground, we actually have to check below this threshold now. When we pull it into Resonite, we reassign it. And you'll notice we have a new input. So I have to grab my inspector. And then in the inspector, I have to go and grab the radius field. And I'm going to drop it in. Now, if I go and look at the ball, it now should decay, but not fall through the floor. And it looks like it is working. To finish things off, I'm going to just open up the flux, tinker with some of the initial values to add back in some of that lateral motion in X and Z for a little bit more complicated demonstration. And I believe that concludes the tutorial. If you're interested in learning more about ProtoGraph, you can visit the ProtoGraph Showcase world in Resonite. You can view the ProtoGraph documentation website, or you can chat with me in Resonite or on the Discord. Until next time.